Hello folks, I'm here today to educate you about power supplies, where they're to be used, their intended purposes and what they have in common, their pitfalls. So what we have here is a variety of different power supplies and a glass of carrot juice, because carrot juice is healthy, especially when infused with turmeric. So, down to business. Also, let me just double check to make sure I'm recording. Okay, good. I can start my speech. So we've got a variety of different power supplies here, okay? They all produce power. They're all different voltages, but these are all to demonstrate. So right here, I have a couple of DIN rail power supplies, very common. This is a pulse. These are bloody expensive. They're very, very high quality and very well tuned. This is a DIN rail 12-volt power supply. The difference between this and a mean well is a lot more than just price. In fact, because this guy here is like, what, about 60 bucks on average? This guy here is about 400. The weight difference, wow. But anyway, these both do the same thing. So these both produce approximately, well, let's see here, how many watts? This one is 120 watts. This one is 270 watts, which might explain the difference in weight as well. So, yeah. Now, the interesting thing about DIN rail power supplies, and actually, sorry, before I continue, I should say, I will be putting links in the description so you can jump past different parts, because I intend to do a very long, boring explanation here. So you can jump through to the parts that you want, and I'll label them in the description. Anyway, so with these DIN rail power supplies, they are literally just that. They are power supplies, and in fact, one of the pitfalls of power supplies is they typically are not self-resetting. You can get power supplies that are self-resetting, but if you trip one of these guys, either one of these ones in particular, both these power supplies actually behave in the identical manner. They will fault until AC has been removed, and then once you restore AC, they will start to function again. So these guys will actually fail off. They'll fail, what is that, open? I'm not sure exactly what the term is anymore. So to alleviate that issue from occurring, we have to add an additional module here, which is a little UPS. So if you were to take this power supply here and connect it directly to a battery bank, sure, it might work, especially if the batteries are full, because you're going to set the output of this power supply to match the float voltage of your power bank. So if you've got two 12-volt batteries for a 24-volt supply, you'll have 27 volts. So you would set this for 27. 27 divided by 2 is 13.5. The little screw to adjust this is right here in the top. So if you're using a 24-volt plant, it runs at 27. If you're running a 48-volt plant, it will run at 54.4. And that's with standard AGMs like these little guys back here behind me. Okay? These are AGMs. So now, what's the purpose of this UPS module? Well, if you connect this directly to the batteries and say the power goes off at the site, okay? When the power comes back on, you're going to notice that your voltage has decreased because you've consumed power from the batteries. So when the power comes back on, the batteries are going to draw as much current as they can to find a homeostasis. They want to reach equilibrium with the power supply. And since the power supply itself has a set voltage output, the voltage will then brown out a little bit, increasing the amount of current that the power supply is exporting. And once it hits its topple point here, which is 5 amps, it will go offline. Let's see here, 24, yeah. So 5 volts, it'll topple. So what this little UPS unit does is a couple of things, and this is where they're important. Now, I'm going to go to another power supply after that's very similar to this. So this is just a regular power supply. This is a UPS. What this UPS module actually does is it limits the charging current. This ensures that you can't topple the power supply. So this, I believe, this specific unit limits the charging current to 2 amps, which is about just under half of what the actual total output current of this power supply is. That ensures that this power supply won't topple if you have loaded it properly. The other thing that this power supply does, or this UPS module, is it does low voltage disconnect, or LVD. LVD is critical. What it does is it ensures that your load is disconnected when your battery voltage drops to depletion. So typically, if we look at, say, a 12 volt, we'll just use that as a common because you can do the math with it, right? 13.5, 14.2, 12.8, whatever, right? So when your battery reaches depleted, which is, I'm bad, I usually go about 10.5, 10.5 volts, your LVD should disconnect. It should cut power to the site to stop the battery from draining well below half. So with AGMs, we don't want to go anywhere below half, right? Lithium ion phosphate, different battery chemistries, you can actually deplete them right down to nothing and then bring them back up. But there's still that bottom voltage cutoff. So this does two important things. Overcurrent protection, so it'll ensure that your batteries have a limited charging current so you don't topple your power plant. And the second is low voltage disconnect. That's why it's got a battery connector and a DC connector, and supervisory contacts on the top, which you can connect into a site monitor, which will allow you notification when certain actions occur, all right? So now that I've explained a power supply and what will happen if you connect it directly to batteries, oh yeah, just to beat that dead horse. If you connect either one of these power supplies directly to a battery and the battery tries to charge itself from depletion, these guys will fault and they will not return to operation until mains is disconnected and reconnected, okay? So now, let's go to a power supply that came out of an RV or a caravan or a trailer, depending on the part of the world that you're from. I wanted to use an Iota, but I couldn't find my Iota. I actually had an Iota 50 amp kicking around here. So this is a 12 volt 50 amp, okay? This is pretty standard in most camper trailers, caravans, whatever you want to call it, right? Depending on your region. Aluminium. Anyway, if you'll notice here, this has an AC plug on it, right? And it's got a DC power connector on it. So this guy here, the output on this guy is actually 13.5 volts DC. Some of these can be adjusted up to 14.2. Depending on what the trailer came with, but typically they're about 13.5 float. These kind of things usually also have multi-stage charging in them. This particular one is a newer one, so it is actually a switching power supply. But here's the thing. These things will auto-reset. Now the catch is, so here's how these guys work. If the batteries run right down to nothing, these guys can provide up to 50 amps, right? You might think that's a good thing. It's a charging source, right? There is no low voltage disconnect on here. This just has a power output that connects to your batteries. So in all essence, what you end up with is this connected directly to here. Now, where the problem comes in is when your batteries start to deplete. So say that your batteries have reached the depletion point, right? You've been running on battery for about 6 hours or so. Your batteries are depleted, right? Now, these 12 volt batteries, without the low voltage disconnect, they'll hit about 10.5 volts, but they'll keep going. Unless the devices that are connected, actually Netonic switches, by the way, have a low voltage disconnect set point built into them, which is very handy and very brilliant on Netonic's part. But unless there's LVD built into the device will take the batteries right down to zero. With AGMs that causes sulfation, with the devices themselves, that means that the voltage has dropped well below their expected voltage, which means that the current internally will increase, which works the circuits a lot harder. And in some cases, if the circuits don't have overcurrent protection, will not only brown out the device, but you can actually blow voltage regulators. So you have to be very, 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 very careful to keep the devices within their operating range, their swing range. So when you're looking at 48 volt devices, the typical cutoff on those guys is about what is it, 10.5, 21. So I think it's 42 volts. I could be wrong on that. I'm going off the top of my head right now. Look up the swing voltage for a 48 volt DC site, and it'll show you the high, 54.4 at full, and it'll show you the depleted voltage. But now I'm going to get back to the point. So you've got a 48 volt site. You're just using one of these guys here to charge your batteries. You've got no overcurrent protection. You've got no low voltage disconnect. This thing will not trip. If the batteries are right down to dead, right, this thing will just ting, ting, ting. It'll shut itself off every time it overheats and then come back on. It'll charge the batteries. That's okay and all, but your 48 volt site might even get as low as 20 volts. And that really causes hard sulfation on the plates. It very much reduces the lifespan of your batteries drastically. And not only that, but you can actually damage them by taking them that low. So it is critical not only have your overcurrent protection, but to have your low voltage disconnect. This does not have low voltage disconnect because this simply is a charger. It's got AC in and DC out. There's no load connector on it. Now, a workaround for something like that, and I'm not suggesting you do that because this is the worst thing, nearly, that you can do. Actually, the worst thing is using those AAA APS 750s at your site. God, that's horrible. But we'll get to that shortly. So one of the workarounds for this is that you can actually add like a solar charge controller. Could be PWM, could be MPPT. But then, of course, you've got to concern yourself with how clean the switching is in that solar charge controller. Because with PWM, you're relying on pulse width modulation. And MPPT, it's using buck boost conversion to actually allow the input source to run at the highest voltages can while matching the output's voltage with the load and the battery bank that it's connected to. So you could put a solar charge controller on this thing, which would also give you your low voltage disconnect. It would give you overcurrent protection and all those functions that you would want to keep your stuff safe, okay? This is what an iota looks like on the inside, by the way. That's an iota DC power supply for a caravan or RV, whatever you want to call it. Okay. All right, so now let's take a look at some bigger things. And by the way, I really want to show you guys a proper shelf rectifier, like an LTEC or an ICT or an Alpha or a Nokia or a Valair, but we're not there yet. I don't have that stuff for my lab yet, and I'm hoping to get some. So now, let's take a look at my favorite power supply, the ALG Com. So now, by the way, I'd like to make a correction on this. This comes with a 15 amp fuse, and I seem to recall previously when I read the manual that this said that it had 10 amp load, 5 amp charging. That is incorrect. This is 10 amp total current ability. That's it. So you've got up to 5 amps charging and 5 amps for load. Now, of course, you can pull more than that for the load, but it's got 5 amps current limiting for the actual load, okay? So this little guy here is a small site rectifier. It's actually a UPS, I guess would be the better term, because a true rectifier is basically like this. So, and that doesn't detract from what I said earlier, because I'll go into more details about rectifiers shortly, okay? So a full rectifier might be something that resembles a UPS. Essentially, with a rectifier, you've got like a full shelf unit. It's usually 2U with multiple power supplies in it. They're usually 1,000-watt power supplies. You usually stack them 3 or 4. And then you've also got a power management module, which handles the low voltage disconnect on the site. You don't have to worry too much about overcurrent because that's built into your breakers and your PDU, which we have something similar here. So now this is what I would use for a small site. I wouldn't use this in a bigger site than something that's, say, running 300-400 watts. Now this is rated to handle 540 watts total, or 480 watts safely, but I like to keep it small. So this has low voltage disconnect and it's got overcurrent. Now this one also has SNMP in it. So your battery connects here, okay? And then I hope you can see that clearly, by the way, because I don't want to pick this thing up. You've seen it 1,000 times, and you'll see it again when I do a video on it, okay? So you've got your battery connector here, you've got output 2 and output 1. Now, the battery connects down here, and so I've got my battery bank here for my test lab here. When your load connects here, it allows the load to disconnect when your batteries are depleted, and it limits the amount of currents that go to the battery, or current that goes to the batteries while the batteries are being charged by the device. So this ensures complete power management of the site. That's its intended purpose as a UPS. Now, if you go with a full site rectifier, your rectifier will usually have additional power management modules that you can either pop into them or you use an additional shelf that has your PDU. This is an example of a small site PDU. So you've got your input voltage right here. There's a 15 amp master fuse, and then you've got 1, 2, 3, 4, 5 fused outputs on it, which you can change the fuses on appropriately depending on the connected load. Okay. So now, with that being said, if I had a shelf rectifier here to show you, like an L-Tech or an Alpha or a Newman or whatever, you would see that it's got multiple power supply modules in it and usually a section of breakers. If all the slots are occupied with power supplies, you would have an additional shelf unit that would have breakers in it, and you would have your terminals on the back. The breakers act as the overcurrent protection, and the LVD is built into it that it will take the site offline when your batteries are depleted, depending on your battery chemistry, whether they're AGM, gel, lithium iron phosphate, whatever you're using on site. So now we've discussed the large rectifier, the small plant rectifier, or UPS in this case here, AC in, DC 48 volts out. And FYI, these power supplies are isolated. That means that they don't have a true ground reference. So if you've got a negative or positive 48 volt site, these will be compatible regardless, because the chassis and your negative, it's kind of floats, I guess, because let me explain it like this. With a negative 48 volt site, your ground reference is positive. With straight up 48 volts, your ground reference is negative. So think European vehicle versus North American vehicle. North American vehicles, your negative from your battery goes to the chassis, and European vehicles, typically the positive goes to the chassis. If I got that wrong, comment below, but that's how I remember European vehicles to be. Okay, so now, that being said, we've covered DIN rail power supplies. We've covered rectifiers and small plant rectifiers. Now I want to talk about what I consider to be no-nos. Okay, now this is a Xantrex, and I like Xantrex. They're a very well-known, well-established brand. Okay, this is a Freedom HF inverter charger. I actually have a fairly substantial Renogy pure sine wave inverter charger in my basement, which keeps the lab and the office energized when we have long power outages, which are becoming more frequent due to severe weather swings that nobody could have expected. So this guy here, you've got your battery connection on the back, 12 volts. You've got your AC in here and your AC out here. So in all essence, this behaves the way a line interactive, excuse me, my carrot juice is coming up. This behaves in the same way that a line interactive UPS would. Okay? A line interactive UPS is essentially just an over-glorified standby. So what it has is it's got a relay in it. That relay switches fairly fast. Your center, your common on the relay connects to your load, and then say, I'm just going to say this arbitrarily, your normally open would be connected to mains, and your normally closed to be connected to the inverter. What will happen is if the power fails, the coil loses is no longer energized, and then it'll fall back to its default state, which is running off the inverter, which then, when it switches over to that inverter, depending on how it's built, you'll have a minor surge as your devices connected resync with the new power source, because you have to remember, AC is alternating current, and we've got two AC sources. They're probably not going to be synced up. They're going to be out of phase with each other. So when you slam over to your inverter, there's not only the relay has to click over, and you have a massive surge load on the inverter itself, whether it's one of these guys or a UPS. UPS are designed to handle that better. But yeah, any way you look at it, there's multiple reasons where you will see a small surge brownout dip, right? In some cases, it can actually cause problems like servers going offline. It can cause your equipment to go offline, which is why it's best to use the appropriate equipment. In this case here, would you connect servers to a Freedom HF? Probably not. Would you connect connect servers to a Renogy inverter or an Outback inverter? Probably not. You're going to use Emerson, Alpha, Eaton, or UPS, and God forbid use Triplite. So, that's the sort of thing that you want to be careful of. You want to be mindful of. So when you're looking at powering a tower site, when you're looking at powering a tower site, say like this one over here, you can't see it. You're going to want to have everything run off DC. Historically, telecom has been DC, okay? From the inceptions of telephone. Once it started to get commercialized and common, we found that telephone systems were 48 volts with a ring voltage of 96 volts. That's kind of how things standardized, and because all the plants were already powered by 48 volt systems, everything adapted to that. The precedence was set way back when. So when you look at most of the equipment that we run, like, let me see if I can dig out one of these Cisco. Oh, I got one over here actually. Let me just squeeze by here and I'll grab my Cisco switch that's sitting on the floor. Okay. So if we look at telecom gear, not only is telecom gear typically hardened, but it's also designed to run on DC. So as an example, here is a Cisco switch. You'll notice on the back here, it's got a 48 volt DC connector, okay? This one's actually 12 volts, 13 amps, but regardless, you get the idea. If you look at stuff like, you can't see it down here, but I actually have a Nokia mid-span injector on the bottom shelf there. It actually has a 54 volt input on the back of it. A couple of these Cisco switches over here are also 54 volts, and most of these Cisco routers, you can pop the power supplies out of them and put 48 volt power supplies in them. 48 volts is the common voltage of telecom. So when you go to a Rogers or AT&T, Verizon, Spectrum, Bell, T-Mobile, Telus, if you go to any of those cellular phone sites and you walk in, they typically have a rack or mini racks of batteries. You'll see rectifiers in those racks as well, and you'll see PDUs, power distribution units with manual supervision. They'll have little contacts that can go. Usually what they'll do, by the way, in all honesty, they'll take a zone on the alarm system and tie it into the supervisory circuit as a chain. And if any one of those breakers pop, the alarm goes off on that zone and notifies whoever's monitoring it. That's typically what they do. The more resolution that they have, the better, of course. So anytime you walk into those shelters for like a telecom tower, you might see like a rack of gel cells, 2 volt forklift batteries ultimately, and you'll see them chained up in 24 cells, which gives you your 48 volts. Or you might see a bunch of FL12s, which are big, long, skinny batteries with a rope on the front and back, and they've got front terminals. And you'll see those guys banked up in sets of 4. So you go 4, 8, 12, 16, all the way up your rack. And you'll see them have little steel bus bars with plastic covers over them, and then a cable on the end or bus bar on the end that goes up the rack. And then that connects into your rectifier. Now the reason why they run that is because inherently all this equipment is designed to run on DC. And if it's specific to telecom, it will have a 48 volt input on the back of it, or at the very least a 12 volt input on the back of it. That's to tie it into a DC plant. If all the devices are tied into the same DC source, there's less likelihood that you're going to see problems like voltage differential across devices that might cause damage to said devices. The DC plant is also far more resilient to power surge, whether it's from EMF, lightning, or from mains, okay? Because you've got this massive battery bank there, right? Like even looking at this chunky boy, this is just one little 33 amp hour cell. But you got to think, it takes a lot of current to affect this thing, okay? The bigger the battery, the harder it is to cause a fluctuation in the voltage with an external influence, unless you drop a fucking wrench or a pipe on it, right? Obviously. So inherently, you're getting wicked surge protection and buffer out of your batteries to make sure that you're always very gracefully within a certain swing range, okay? That's one of the big important things. The other thing as well is when you've got a simpler plant where you've got like a rectifier connected to these batteries that, as I said, are inherently natural surge protectors, right? It's harder for you to pop the rectifier unless lightning comes straight through the plant, which if it's properly grounded is a very low likelihood. Not impossible, but very low likelihood. So your gear is less likely to fault or fail during a storm. So that's another reason why we go with DC plant, okay? You get longer runtime as well, because if you're using inverters, you're stepping your voltage up to 120 just to connect it to a power supply to bring it back down to 48. So you're doing double conversion on that just to power your devices, which you're losing as much as 30% of your site efficiency by doing that. That's why we typically don't run inverters on site. So now let's get down to these guys. So one of the biggest mistakes I see people make, and I say mistakes because it is a small provider will take something like a AAA APS 750 or this Epic Xantrex Freedom, and they'll misuse it by using it to power their site. So now you're taking 12 volts, which, by the way, when this inverter is running by itself, it can draw 5 to 10 amps. Yeah, it can waste a lot of power when it's running just being idle. And if you lightly load it, it's very, very inefficient. So when you're choosing an inverter for powering a whatever, like say it's for your RV or whatever, you want to make sure that if you've got a constant load, you keep your inverter about 20% larger than that constant load, which will keep your efficiency up. Okay, but that's just one tactic. Obviously, if you're living in an RV or like me, you've got a backup system, you want a big one to make sure that you can cover all the loads that are going to be in your house. But back to the point. You've got a 12-volt battery connected to this thing, okay? So you now have to convert that to 120 volts in our case, because we're in North America, 240 if you're overseas, okay? So you're stepping that all the way up using complex switching circuitry, which is sensitive, by the way, to EMF, ESD, whatever, right? You can pop this very easily with lightning or inductive flux, right? So you have to be very careful with this equipment, right? And on top of that, it produces noise because this is switching circuitry. This is circuitry that is boosting a voltage and then switching it so fast that it creates, I don't believe that this is pure sine wave. I'm not sure if it is or not, but if it's modified sine wave, it's even worse because you get a signal that looks like this. It's a billion little squares all put together that create your sinusoidal wave. It's a simulated sinusoidal wave. It's not a true sinusoidal wave. Whereas on a pure sine wave inverter, you usually see a nice, clean wave, okay? So that's another thing you have to consider as well, is that you can get RF noise from this that can either damage your circuitry, which has not happened very often, but it can. It can wear down circuitry. Actually, I'll give you a great example of where it can cause damage. If you've got an electric motor, which you're probably not running electric motors at your site unless it's for your air conditioning or whatever. If it's running off the inverter and it's a modified sine wave inverter, because this is not pure sine wave, the motor does not run as efficiently. So its power factor goes out the window. And that can actually damage any control circuitry that's connected to the motor or damage the motor and its windings itself. So that's why when you're running a motor like that, you need to run it on a pure sine wave inverter or a generator. So there's another example. You've got noise, you've got inefficiency, you've got potential voltage differential as well. If you touch the neutral on this while this thing's running and it's not connected to mains, there's a pretty good chance it'll lift you. You'll get a hell of a shock off that thing because it's a floating neutral. You have to remember, this is basically simulating power. It's boosting and converting it to AC. It's not mains. The national grid, you'll notice that most electrical poles or generating stations have a reference to ground. They've got a pole that goes straight down into the earth, a ground rod. Most electrical poles, most generating stations, your power panel itself. That's why earth ground is called what it is. That's why it's called bonding to earth or ground. These guys here float. Okay, so not only is the neutral not common to the ground like it is in our national grid, but the neutral just floats in general because like the way that it's actually generating the electricity. Okay, so there's no true reference to ground here. So you can get a shock and it can generate a lot of noise that can affect your plant. So using a power supply like this is very detrimental to your plant, and I highly strongly advise that you avoid doing so. Another thing as well is it has no supervision. You'll notice that on this little small plant rectifier, this UPS, there is a Ethernet port for SNMP. You can monitor it. You can get full supervision on it. You can find out what the battery voltage is. You can find out if you're on mains or not. You can find out what your load is. All those things. You're blind with this, and you have to add an additional piece of hardware known as a site monitor to be able to monitor it. So now you're spending even more money to band-aid and cobble something together rather than just pay less or equal to for the proper equipment in the first place. Okay, so now, Inverter charger's bad. Never use an inverter charger at any of your sites. If you want to argue the point, go talk to a master electrician. And I mean a master electrician, or somebody who specializes in data centers and telecommunications technology. Not Bob down the street who's wiring houses on the side, okay? So anyway, UPSs are not great to use at a site, but they're still far better than inverter chargers for many reasons. But I will give you the benefits and the pitfalls. There's no true benefit to using a UPS at a telecom site, okay? So when I'm talking to a lot of people who ask me, oh, well, I want to run a server here. Well, no. How much bandwidth is the server going to require? Is it a Netflix server? Is it a, an AWS server? Is it something like that that requires a lot of bandwidth? No. Put it in your office. Your office has UPSs and a generator. It's going to have better runtime there, okay? Oh, you do have a Netflix server? You do have this and that? Well, then your network is probably quite substantial, and your head end will probably have a couple of Eaton or Emerson UPSs with a standby generator from Guardian, Generac, Cat, whoever. Now, in situations like that where you have to use a UPS because you've got servers and whatnot, you typically have a UPS that's just enough to hold out for about 5-10 minutes. That's typically what UPSs are designed for. 5-10 minutes, unless you're talking special circumstances where you've got like a large Emerson plant that stands as tall as you. The point is that the UPS is to carry the equipment over until the generator has started and the circuit switches over to the generator. And in cases like that, you also want to make sure that you tune your UPS appropriately. On the back of your UPS is usually a calibration button. You push it and hold it in accordance to what the manual states, and that allows it to watch your signal. It allows it to adjust its sensitivity to how clean or dirty the power is. And you don't only want to do that with your site, you want to do that off the generator. Because if you don't do that off the generator, what'll happen is, if you've got, say, a fresh APC is horrible for this. I don't like APC either. You plug in a fresh APC, you don't calibrate your UPS to your generator. Mains fails, and the UPS is like, whoa, that's dirty power. And it's going click, 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 trying to come online, but it doesn't want to because it says that the power's dirty. There's something wrong with this electricity. I don't know what it is because nobody calibrated it. If you run the generator and push the calibration button and hold it, or sometimes through the software you can calibrate it remotely, that will allow the UPS to get used to the power that's there and say, okay, it's fine, I can run on this. So those are some points with UPSs. Now, something else that's a big difference from a UPS to an inverter is UPSs also have supervisory circuitry in them. They usually have an Ethernet monitoring card that allows you to, the same thing as over here, monitor via SNMP site voltage, battery status, load, everything that has to do with the UPS, test cycles, logs, all sorts of important factors, temperatures that you need to know from this that you can't get from this Freedom or from my beautiful Renogy or any other awesome inverter charger. You just can't get those stats from there, and then you have to add a site monitor. The other thing as well is this just has a simple relay to click over, whereas this might be double conversion, it might be line interactive, right? It could be a few different flavors of UPS, depending on what you need for your application. When you're running servers in that, you want something like a double conversion UPS, where it's actually taking the AC and then running it, converting it to DC, going through the batteries, and then running the inverter off of it at the same time. So when you do things like this, what you end up getting is you're actually running all of your equipment off of the inverter inside the UPS, which is usually a very clean, pure sine wave inverter, and running it off the AC to DC power supply. That's typically what you get. So you're talking about UPSs, right? So that's kind of what you have to consider. UPSs are far better than inverter chargers, but they're still not appropriate for a telecommunications site, unless you're talking about a head end where you've got a generator, etc., right? So I think I've beaten this into the ground now. This guy's relatively heavy too, and I don't want to pick it up. So that being said, just be mindful. Remember, your sites, your telecom sites, are designed for 48 volts. If you're using equipment that's all AC, like you buy a switch that's AC, chances are that switch is not appropriate for the job. You need to make sure that the switches that you use have DC input. In a lot of cases, we adapt switches. So I'll give you a great example. A very common switch what to recommend to people is Microtech CRS328, which is beautiful. It's a beautiful switch, but the problem is they never made it with a modular power supply. It's AC only. So you end up having to take the power supply out of it and put an adapted power supply, usually a buck or boost converter, which will appropriately adapt it to the site, okay? But for the most part, most telecommunications equipment is inherently DC and has DC connectors on it. This is why we run our sites at 48 volts. And with smaller stuff, when you're looking at SOHO or entry-level telecom like Ubiquiti stuff, it's usually 24 volts. But when you're picking your site voltage, if it's an itty-bitty little site and you've got all 24 volt stuff, sure, use 24 volts. But if you're running a more substantial site where in the future you're probably going to be running like base cells, Airspan, Nokia, EMBs, or Tarana, you want to just start off with 48 volts. You want to build it properly. You're probably also not going to want to go with this if it's going to be a bigger site. You're going to want to go with an LTEC, ICT, whatever, a full shelf rectification kit, which is not going to be cheap. But if you're spending the money on all that equipment, you want to power your equipment properly with the appropriate tech to make sure you get longevity out of it. Okay, so that's everything I need to tell you. I will touch back on the UPS stuff again for a second. I forgot to mention, with all the conversion that's occurring inside of these UPSs, they are also sensitive. You will get far more stability, reliability, and functionality out of a DC site than you will out of a site with a UPS, because this UPS as well, one lightning hit and chances are it is done. These batteries here, they'll take multiple hits all day, and in fact, I've had a couple of sites get blown up by lightning, and I walked in and the batteries were perfectly fine. Now, that being said, I have also seen sites where the batteries were blown to pieces as well. Okay, but the point is that these batteries are such rude technology, they'll put up with a lot more hell than this beautiful, pretty little Eaton UPS. And this guy here is behind those batteries. So there you go. There is my little in a nutshell what power supplies to use where. And one last thing I should bring up, I don't know if I've got one here. Another no-no is cobbling a site together with a charger, like a small, what's a good example of that? Like an e-bike charger or a scooter charger. Say, oh, you're thinking to yourself, well, it's a charger, it's good enough. Maybe if you're running a couple of radios and it's just a little hacky relay up on top of a hill or something, right? And you just need just enough power to power those two radios, you might be able to squeak by that, but that's still inappropriate. That's a small enough site that you can use something like this. You use a little kit like this, it's cheap enough, it gets the job done. And this is still like a fraction of the price of one of these guys, which you would use at your typical WISP site. And then when you go to a much larger site where you've got a bunch of Tarana gear and base cells gear and all that, that's when you move up to using rectifiers, shelf rectifiers, okay? So there you go. Remember, inverter chargers are no-nos. Trailers of power supplies are no-nos. You want to use proper rectifiers. And if you're running servers in that, use good quality UPSs like Eaton, Alpha, Emerson. Or Magnesine's pretty good too, but yeah, avoid like APC or Triplite in my personal opinion, okay? That's basically all I've got to say for now. If you guys have any more questions regarding DC plant, by all means, just hit me up in the comments below. If there's anything I said wrong in the video, please tell me in the comments below so I can correct that information and the rest of the community can see the corrected information in the comments, because these videos are to help you guys. So if other people have insight and information, please share it in the comments below so that we can all grow together. So anyway, thanks for watching, guys. And don't forget to like and subscribe. And if you really like the content, you want to help keep me fed, then, which also helps me buy equipment like this for tutorials and whatnot, join the Patreon. Anyway, thanks for watching, guys. I know I left some stuff out, but whatever. I can keep making videos, right? I mean, I'm still alive. Ugh. Catch you later.